it's got this price point where the threshold is just too high to actually scale it and fan it out, which is what the promise of web services is supposed to be all about. And it fundamentally comes down to the difficulty of dealing with the XML. So, being good researchers, we realized that we could generalize this to a general problem rather than the specifics of an e-payment, e-contract problem, and look at the whole issue of XML infrastructure and the processing of XML and solving this economic deficit that we were finding. History wasn't on our side. HP in 2002 took a strategic decision to shut down its middleware operation, which left us with an XML technology stack with no place to go. So we founded 1060 Research and took it out and have commercialized the concepts as 1060 Net Kernel. So what we're talking about is fundamentally an XML procedural mismatch. If you look at XML messaging, it can be characterized as really three things. There's a parsing phase, some sort of transformation, and serialization. And it doesn't matter which of these stages you look at, there are some fundamental difficulties with handling the XML. Which object model do you choose? Object models, when we started, were very immature. There's been a proliferation of them, but they're still basically kludgy APIs that allow you to create object bindings for the XML structure. More subtle problems. There's issues with thread safety in a lot of these XML technologies. Debugging and exception handling of large dispersed collections of objects that represent XML structures are very, very tricky. It's almost impossible to get your head around where you start debugging. Now, all of these problems are surmountable, but it leaves you with a fundamental issue, which is this procedural binding of XML leaves you with a brittle system, something that can't be changed, even though the XML can be readily changed. And we were realizing that this is just history. You know, this is something we've all seen before. And if we look back and we see the history of the relational database, what we had in the 70s was early relational data models where essentially they were built as bespoke custom applications. Each was a set of procedures. Each part of the database was a brittle component. And what happened to change that model, to make the data model fit with the business process, was the introduction of a declarative abstraction, the introduction of SQL to allow you to rapidly and flexibly change your data representation to suit your business without having to worry about how you actually implemented the internals of this system. Our feeling is, and still is, that XML's at that stage. It's still at that pre-abstraction phase where it's still real hard to do stuff with it. Step forward, net kernel. This was the problem that we basically started developing a system to solve. In the best traditions of software systems, we threw the first two away, and net kernel is the result of 5 years of figuring out just how these systems really should mesh together. What we've come up with is an architecture where software components, individual internal software components, are essentially micro web services. We actually invented these before the web service term came about, so they're URI addressable software components. That's the fundamental abstract model. Each software component and the URI for a software component is published in an internal address space, just like a web system. So what we have is a web of software components. Once you've got your services exposed as URIs, you can go up to a higher level and you can sequence these into pipelines. So what we have is the Unix-like abstraction of treating software components as self-contained specialist units and then allowing you to build higher-level applications by sequencing and combining them together. So this is the web meets Unix. URI addressing meets sequencing and scheduling along the ideas of Unix pipeline model. And Unix, if you think about it, is really the origins of this phrase loose coupling. That is what the Unix abstraction really gives you. It gives you the ability to very rapidly change software systems around. Part of the value of the system is that services aren't just facing outwards. They're not just servers. Every single URI addressable service component is both a client and a server. What that means is that basically higher level language runtimes, scripting languages, declarative languages, are essentially services that execute code, but each of those services can invoke subservices. So they can call out and sequence together lesser services, if you like. What this means is you can create complex assemblies of URI addressable software components, all of which, when you've built an assembly, can be abstracted behind another URI, which basically is then a higher order service which can be used by another service, etc., etc. So the URI address space of the web gives you an extremely flexible way of combining together software components. This is service-oriented development, but applied to the very finest grains of software composition. The advantage is that you can take any software component at any layer in the system and very easily just expose it onto an external transport. So you can take an XML message processing service that's maybe involved in some sub-process and expose it as a web service because it's an XML interface. It just needs to have a transport bound to it. In NetKernel, essentially, it's services all the way down. There's nothing but services. Services encapsulate object models. You can use your preferred object model, etc., inside the service. So I have to tell you some of the detail about how we do the addressing, because this is the key to how NetKernel actually sequences and schedules services. But fortunately, the last line says that you don't have to do this. You can keep this under the hood, but you need to know something about why we do this. What we've come up with is basically a very simple syntax for a URI. It's a URI we call an active URI, and what it is, it's a multi-part URI. It's characterized by some service base path, service URI, and then an indefinite number of named arguments. Argument 1 with a value, which is a URI. So this is a URI. Argument 2 has another URI attached with it. The arguments, since any argument can be a URI, then it could be another active URI. What this means is that URI becomes essentially a deeply nested functional program. It describes a sequence of service invocations as a single self-contained functional program, which can be lazily evaluated by the kernel when the request is made for that resource. That all sounds somewhat esoteric and advanced, but it's not that complicated, really. So an example of a technology that you can wrap as a service is something like an XSLT transform. It's just a software component. It's implemented by some intrinsic object model and API, and is exposed just as a URI. So here's an example of a service, active XSLT. Here's a named argument, happens to be called operand. It could be anything. MyMessage.xml, and I apply an operator to it, myTransform.xsl. So this active URI completely describes the result of the transformation myTransform upon myMessage. Because the URI is both the program that executes the result of that service, it's also a unique URI key to the result of that service. What that means is it's a vector to the result. If the result has been pre-computed at any point in the past, just like in the web, it's just a resource at a URI location, which means that it's cacheable. What that means within the system is that the system, when you build up a complex assembly of services, if any computation has already been pre-computed, it's never recomputed because it's already known in advance in the cache. The caching model in NetKernel is a dependency-based cache, which means that it keeps a record of all the metadata about all the dependent resources that go into generating any given resource. It therefore invalidates anything if anything is changed. So you end up with a self-optimizing system where you guarantee to do the least amount of computation to combine any set of software components. It was a nice side effect. We didn't expect it, but it just turned out that way. What we're really talking about with NetKernel is we're using the same fundamental abstraction as the web. The reason the web scales, the reason the URI address space scales horizontally and vertically, is because the URI address space is effectively infinitely large. You can always add more space into it. And this is what the active URI addressing model gives you for any technology. So, why did we come to an active URI addressing model? Well, it turns out that the XML technology set essentially assumes there's an implicit URI addressing model out there. It kind of expects there to be a URI resolver that'll get me the resource. So you can do includes into a document. You can do XSL include. You can include a document function in an XSL transform. You can do includes into an X query. But there's no realization of that URI infrastructure. Where is it? Netkernel is that URI scheduler, effectively. Like I said, we don't deal with active URIs when we're handling this stuff because working with them would be unfeasible. You can't think of these things. What you do is you use higher-level languages that build these things up for you. Okay, that's the fundamentals. Okay, it's time to do the high wire trick. If I get this right, you'll think I've staged it, and if I get it wrong, you'll all be able to laugh anyway, so let's see. So I'm going to show you some real stuff because I think that's the best way of understanding anything. So what I've got here is a language called DPML, Declarative Process Markup Language. And DPML is a declarative language for writing active URIs. That's effectively what it is. Or a language for creating service invocations of software components. So here we have, and you could think if you're coming at this from a very strict web service background, you could think of this as like a micro BEPL. We had it before BEPL came along, but what it does is it's a declarative way of sequencing services. You can actually use it to call web services, which I'll show you later as well. Here we've got a single instruction. It applies an XSLT here to my first data, and it applies my first transform. It's then targeting a special URI called the response, this response, which says, from this DPML service, send me the result of whatever this execution is. So if I run that, we end up, I need to show you the data, I guess, to make it make sense. My first data is just a set of stupid data, red, green, blue. And my first transform is just an HTML styling of that data into a set of 3 tables, each of which uses the color attribute to figure out what the color should be. Okay, that's not very exciting, but it produces 3 color boxes on the screen. More exciting is if I show you a 2-stage transform. So what we can do is we can take the results of a first XSLT transform, in this case a color filter, select the blue out of the data set. We target a variable, var, here, which the DPML runtime manages the state of. That variable is then passed to the XSLT transform here. Everything is addressed by URI, so this is just the URI to the variable. Here we're just saying that's the source of this operation. So what we've done is we've applied a filter on the start of the data and applied the same data to the second. So if I select blue, we get blue. I could equally, because everything is dynamically evaluated, no, cancel that. Well, I didn't get the recording I was after anyway. That changes it to, did I save it? No. Changes it to red. So you can see how very easy it is to take something like an XSLT, which is a very common XML technology, turn it into a multi-stage process. Okay. What we're really talking about here, though, is what do we mean when we talk about web services? And fundamentally, if we go back and think, the web service, the fundamental driver behind the web service is the exchange of XML messages. And the reason we're doing that is because the XML is a flexible structure to put our business data in. The problem we've got is when the data comes through, when the message arrives on the system, comes through your web service star stack on the outside of your system, how do you deal with that document when you finally got it as a message? And the SOAP message body, the SOAP structure, SOAP 1.1 or 1.2, whichever of those you look at as your foundational SOAP message type, is a pretty arcane thing to deal with in terms of procedural code bound to it. So here's a web service written in netkernel. That's the client. This is a service. This is the echo service. So I'm copying a parameter, this param, and it's called message. It's a request that comes in on the active URI message. I'm sending it to the response. That's it. That's an echo service on netkernel. Here's a client that'll call that. This is This is using an accessor. We call these services components. We call them accessors. Here we're calling the web service SOAP client. We're invoking it with an endpoint here, the test echo service. The action is described here. We're passing it dynamically a configuration file so that it can understand what client binding to use. In this case, it'll use the HTTP binding, but it could be SMTP, it could be an arbitrary protocol, it could be JMS binding. And then here, I'm showing an aspect of DPML, which is that any argument can be a literal inline XML resource as well. So here, this is just a convenience. This could be a URI reference to the message, or it could be inlined. So here, I'm sending a SOAP message to the service. Mary had a little lamb. Finally, when the service comes back with its result, I'm applying a transform to it just to visualize the XML for browsers that don't support it natively. So if I go to echo, I run that service. That's invoked it. So what I've done is netkernel is providing both the service. It's bound to an HTTP protocol, that SOAP service I showed you, which is the copy instruction. That instruction is returning this SOAP message. The HTTP binding is all getting taken care of by another service that's not shown. And the client is invoking it, and it's two instructions to invoke it, and one instruction for the result. Okay, so that's all very good. But what if something goes wrong in my service? How do I debug web services? How do I look at the XML and treat it in a way that allows me to intercept and manage this service invocation model? So what if, for example, my SOAP client is returning a result that I didn't expect? So in this case, Mary had a little dog, and I was expecting lamb. Not something that a schema could deal with, because this is semantic problem with the data. How do I go and look around in my service model and find out which part of my system's failing me? What I can do is I can use something in the netkernel system, which is the idea of a breakpoint, but applied to a web address space. So if I go into the debugger, I can add a breakpoint, active SOAP client. What this is going to do, the kernel is going to now, whenever a request is made for the service that matches that regular expression, .star active web service SOAP client .star, it'll intercept it and allow me to inspect the state of that request. So if I go back to my service and try that again, nothing happens. If I go over to my breakpoints, I can go look at my stopped requests. Here you can see the active URI. It's the first time it's been revealed in public. I can go and look at what's going on with that request. Here I can see the call stack that's going on through this service address space. Here we can see the request came in through the HTTP transport. It was invoking the DPML engine, running the echo client 2, and we finally see that it's an active web service SOAP client with all of these arguments attached to it. All of it's been escaped, obviously, because we're not touching that by hand. Over on the request side, we can see the result. Okay, right, the service has brought me back. Mary had a little dog. Right, something's going wrong. Not right. But I can see The dependencies, it depends on a metadata implementation, but that's all. There's nothing going wrong with the dependencies. I can see that it's a MIME type of text XML. I can go and see what the arguments were. I can see the message that I invoked it with. Hey, look, the message I invoked it with as a client was sending dog, not lamb. So I'm to blame. So if I go back to my debugger and release that request, the process doesn't know that it's been intercepted, and it just comes straight through. If I go back to the debugger, turn that off because I don't need it anymore. Okay. If I go back into my application and look, I can see, oh yeah, no wonder I'm not getting lamb back. I wasn't putting it in the message I was echoing in the first place. So obviously what you're going to get back is what you'd expect. But I didn't save it. Got to remember to save when you're doing demos. Now we had a little lamb. Okay. So all that's kind of neat because it means you can inspect, deal with your XML message at any point and anywhere within this environment. So you can intercept services within NetKernel, inspect the state of the service invocation, look at the results of the services, go back up the call stack and find out what was going on previously. It allows you to get a handle on where things are going wrong with your XML processing of those SOAP messages. But we currently live in a world of web services which are pretty unstable. No matter what the vendors are telling you, there's still confusion, even down at the very lowest levels. For example, should you use a SOAP 1.1 or a 1.2 message? Doesn't make a lot of difference to a lot of systems, but it certainly does if you're dealing with the XML, because you've got some very different characteristics to it for a doclet service. Turns out that with the NetKernel model, basically that's all I have to do to change my service into a web service using SOAP 1.2. You'll see here, last request, it's using the old namespace. If I invoke it now, it's using the new namespace. All of the services that are SOAP specific, so for example, creating a new SOAP message, adding a body part to it, invoking the SOAP client, there's a whole bunch of other SOAP specific tools that we provide. It has SOAP fault, new SOAP message, add header, delete body part, delete header, etc. Each of these is a component that can be used on the SOAP message. They're all written to be totally independent of 1.1 or 1.2. So the code doesn't change because it's just a service invocation. If the message is a SOAP 1.2 message, deals with it. If it's a SOAP 1.1 message, deals with it. There's no need to adapt your code to worry about the legacy of existing 1.1 clients, etc. Okay. So what we have is a very simple echo service. And I guess if you had £1 for every echo service you'd seen at a web service demo, you'd probably all be millionaires. What would be a more complex service that shows like a real, more typical use of a web service system built on this abstraction? So here we've got a service. I'm going to show you the code first. Here we've got a service which is providing a game engine. And what it's doing is interacting with a relational database, and it's creating a unique game with a service called Create Game Service. And the game is basically a random number guessing game, but it's a two-dimensional one. So you've got to guess a number between 0 and 100, and there's both an X and a Y. So you have to try and guess that two problems. And obviously, everybody knows that you basically use a binary chop algorithm to find the least number of computational ways of getting to it. But how would you implement a client, or implement that game so that you've got a game that creates a service, creates the game, and then has an engine that runs the game so that you can keep asking it, am I getting higher or lower than the value that's being guessed? So what we have here is a game service we're using something called the SQL query service, which is querying everything from the games engine. If this query throws an exception, we're using DPML's exception handling model. Here we've got an exception block. Basically, execution flow moves as soon as an exception occurs inside an instruction, inside a service request. The execution context moves to the first exception block that is the same level of cardinality in the XML. Okay, so execution moves from that instruction block into the exception block, so it starts processing the exception. So what we're doing is, if the select star from games fails, then we just do an SQL update and create the table because the database just doesn't exist. This is just using HSQLDB to create a dynamic in-memory database. We create a GUID for the game. We create a random seed. There's just a service called random seed that's generating the random XY pair. And we style that result into into an SQL statement, which we store the result in the table. And finally, we send a new SOAP message, and we add the body part, which contains all this data out on the message. So if I invoke... actually, I'm not going to show you that because... wrong one. The game service, if I show you the documentation, what the create game does is, here's a request, create the game, and I get back a game ID, which is now a game that is stateful in the database, and we're going to execute that game, make some guesses about what the random numbers are on the X and Y. Okay. If we now look at the client to this game, the client is creating a SOAP 1.1 message. It's issuing this message to the high-low game, and it's using the action create game. So it's initiating a game. It's testing to see if there's SOAP faults. It's testing to see if the SOAP. It's converting the SOAP fault to an exception. So if a service is invoked, it returns a SOAP fault, and you want to throw that as a real net kernel exception up to the services that called this, then we can convert it to an exception dynamically, and we can throw that exception. I'm going to run the game because you're all dying to see what happens. We've got a client that's written to use an optimum algorithm to solve the game. And if I run that, what it does is the guess was obviously 9335, and it computes the least path through. And it's made a sequence of invocations of the SOAP service until it found the result. The client is written with a bit of trickery. Because what it does is it looks at the turn and it says, if the turn is even, then I'll use a SOAP 1.1 message. Sorry, if the turn is odd, I use a SOAP 1.1 message. If the turn is even, if the last guess was odd, then I use a SOAP 1.2 message. You'll notice that the server didn't have any SOAP 1.1 or 1.2, didn't care. The rest of the client doesn't care. All it's doing is that initial seed message is created using, based upon what the result of the last turn was. If we go to the game service itself that's actually running this turn, you'll see that there's no code really to deal with the message. It's just applying simple operations to the message, processing it, moving it into and out of the SQL domain, into and out of the relational data model, and returning a result of everything's correct. It deletes the games. So what we have is, I'll just show that it's real. It runs again. If we look at the log report, you see that I'm not faking those SOAP messages. It's alternating between 1.2, 1.1 messages each time, and the code is essentially independent of that detail. So, in summary, I suppose, what we have is a way of dealing with those SOAP messages. Oh no, I'm going to dive into this. okay, this guy isn't just some crazy fantasist who's telling you that he's come up with this abstraction that works really well for processing soap. Other people think it works too. This is a case study track after all. So what we have is a reference customer, a company called Trimondo, which is a joint venture between Lufthansa and Deutsche Post in Germany. They have a business-to-business portal with 300 vendors and 5.5 million products. And this system was characterized by SOAP doclet messages coming into an architecture which was handling those messages for each transaction. And they'd found that they'd written this system using a procedural binding of the XML message. And they'd essentially painted themselves nicely into a corner. They couldn't move their code to change their business. They'd run out of space, and there was no way that they could move using a traditional J2E approach or a .NET approach. It doesn't matter. They couldn't move their system out of this dilemma. What they've done is they've discovered NetKernel, and they've introduced NetKernel as the SOAP message processing engine inside their portal. And what NetKernel does is it just basically spends all day stripping apart SOAP messages, integrating with their database, their data model, a workflow engine, but also, because NetKernel is a client server, also integrating with external stuff that they've just needed to add as they've gone along. So they've added email processing, they've added fax support, so that the SOAP message is not the be-all and end-all. The SOAP message is just part of an event that generates a whole load of business services like email, websites they're about to add, and fax messages, etc. What they've done is they've taken a phased approach. NetKernel is an embedded system, so whilst I've talked about it essentially as an application server and demonstrated it as an application server standalone, it's a fully embeddable coprocessor effectively, so you can use it within any Java system. It can be embedded inside an application server to basically provide a high-performance XML processing coprocessor. And the experience of Trimondo is that they've moved all their XML message processing over to this system, and what they will do is be migrating to a 100% NetKernel system over time. The result of this system is effectively that they actually can build their system. I mean, that's the net result. Before, they ended up with a system that just wasn't scaling with their business changes. And they've decoupled all of their ability to change their fundamental data formats to allow them to rapidly reconfigure their internal software architecture to cope with those changing messages, which means you've got an adaptable system. So the summary is, what I've described is something we're calling service-oriented development. Service-oriented is a real cliche because it's overused. There are too many people promising the world by describing it as service-oriented. But what NetKernel does is it takes that principle of decoupled software, the ability to flexibly change it, and applies it to the finest granularity of the system. The URI addressing model we have has the same scaling properties as the web, which means that it's cacheable, you can always add more space, and you can always layer a new abstract layer above any previous layer. So you can always add a URI that abstracts the previous URI. This gives you total flexibility in how you configure your software systems. Something I haven't had time to show, but that completes this decoupling, is that this issue of what object model you choose to represent any information, whether it's your XML data or SQL or whatever, is always a problem. And what we've done in the architecture is solve the issue of the object model by having services which dynamically translate from one object model to another. So, for example, if you've got bits on the wire coming in as a binary stream and it's an XML message, and the service really needs SAX or the service really needs DOM, then what the service does is say to the kernel, I need this as DOM. And the kernel then goes and says, where's the service that converts this binary stream to DOM? What those things are usually called is parsers, but a parser is just a service. What we also then have is that any process is just a simple matter of composing any other set of small services. You can always abstract that process and make something more complex look simple by putting an interface over it. More importantly, the service abstraction hides these low-level APIs. You're not grappling with the XML object model APIs. You're not grappling with the individual technologies APIs. You leave that to someone who knows about those APIs. You put it behind an encapsulated interface, and you just compose that together using a higher-level scripted language runtime. It's just like Unix. It's just like Bash scripting. We've applied a general error handling model so that all services, irrespective of their implementing technology, gets an exception handling model provided by the infrastructure. Now, a lot of XML technologies, XSLT, XQuery, don't really talk about error handling in any sophisticated way at all. So what we do is we have an extrinsic service management environment that captures all exceptions and then can handle them and deliver them to an appropriate receiver. What it ultimately gives you is a system where XML message processing is incredibly adaptable. And more importantly, this architecture solves the problem we found 6 years ago, which is the economics now can be made to work when you really do touch the XML. And for any hard-headed developers out there, it's a heck of a lot of fun. It's a real nice way of building systems. Well, that's it. I'll take your questions. Any questions? No questions? Stunned silence? That's about rest. You don't want to know about that. Okay, well, thank you very much.